Hello everyone and welcome back to the channel. In today's video we're going to be building a Retrieval-Augmented Generation, also known as RAG system, entirely from scratch in Python. RAG is the technique that lets your AI have access to your documents. Basically this can be your PDFs, your notes, your knowledge databases, and it can even answer your questions regarding these documents accurately. So if you guys are ready, let's go ahead and begin. So before we start, we need to know what even is RAG, right? So let's start with this problem. Say we have ChatGPT, right? It's incredibly smart, but it has a huge limitation. It only knows what it learned during the training, right? It has no idea what's in your files, what's in your, for example, company's documents, or even your personal notes. So if you ask it something specific, like if you ask it something specific about yourself, or like what does our refund policy say, or summarize this paper I'm reading, it's either going to make something up or just tell you that it doesn't know, it doesn't have access to these documents. And this is not something useful for an LLM to have, right? So this is where RAG comes in. It solves this problem, and the idea is actually very simple. So it just has two extra steps that happen before the AI answered your question. So the first step is retrieval, which is the R in RAG. And instead of sending your question straight to the AI, we first search through the documents and find the pieces of text that are most relevant to what you asked, right? And after this step, we have the second step, which is augmentation, right? So basically we take those relevant pieces that we did from retrieval and we hand them to the AI as an extra content. So we can say that we literally paste them into the prompt and say, hey, use this to answer the question, right? And that's pretty much RAG in short terms. So retrieve relevant information and augment the prompt with it, then generate an answer. It's just two more extra steps we take before having the AI give you the answer to us, right? So one thing to remember here is that the AI isn't trying to actually remember everything it learned. It just reads a small specific piece of text that we give it and summarize it. So this makes it much more accurate and much more easier to use. So therefore, the system we're going to be building today has three main jobs. So number one, it will take our documents and prepare them so they can be searched intelligently by the AI, right? And number two is that when a question comes in, it finds the most relevant parts of these documents. And number three, it just hands these parts to an LLM to give us a real and accurate answer. So now we can start coding it, and today we're going to be doing part one of the first job, which is preparing our documents, and we're also going to be storing the relevant information. And part two, next video, it will cover the searching and answering. So if you guys are ready, let's now head over to our IDE. Okay, so first we need to make a new project folder here, as you can see. So we'll split into two parts, one for .env and rag.py, which is the main file we're going to use. So once we have these, which I will go into detail in a sec, we need to also install the libraries. So the libraries we need is, let's install it here in terminal. So we need pip install OpenAI NumPy and python.env. .env, and actually we need to put a dash here, so python.env. Then we also need PyPDF. Okay, so now we can just install these. And while installing, we need to quickly explain each one. So firstly, we use OpenAI, and obviously this gives us access to the LLM that we're going to use. Next, we use NumPy. This is for vectors, the math, right, for the LLM. And python.env is basically going to keep our API key out of the code. It's just for simplicity purposes. And next, last one we're going to be using is PyPDF, and this will be using to access the PDF files. Then here we come into the .env file. Here, for now, we're just going to keep our OpenAI API key, right? We just store it here. And in the rag.py file, we're going to be using the main code that we're gonna write. Okay, so now that we have this set up, we can just start the next step. So the first step is that we need to load our documents and split them into chunks. So why we need to split them into chunks is because the LLM have a context limit, right? So we cannot just overload it too much. So smaller chunks also make the retrieval much more precise and more efficient. So therefore we're going to be using chunks here. So now we need to write a function that will load the PDF and split it into chunks of, let's say, around 500 characters, right? And we were going to be putting a small overlap between these chunks so we don't lose the context at the boundaries. So let's start this. We can go ahead and start with writing import. First we need OS, then we take from PyPDF import PDF reader. Right, then from .env import load.env. Then we load .env that we just use. Then we need to make the function, right? Define load and chunk. We do PDF path. We set the chunk size. So we do 500 for now. Then we write the overlap. And let's set 50 for now. Then we set the reader. We will set it equal to PDF reader, PDF path, right? Then we set the full text for now. We set blank. Then we make a loop to read all these pages and add to the full text. So we make for page in reader.pages full text plus equal page.extract text. Then we can set a new line each time we take a text in the loop. So we do /n. Now we make a list for the chunks. We select empty right now. Then we set the start index to 0. And now we make another loop while start is less than the length of the full text. End equals start plus chunk size. Okay. Then after we get this, we need to append in each iteration of the loop to the chunks list that we made. So we make chunks.append full text start and end. Then finally we add to the start, so plus equal chunk size minus the overlap. And finally we return the chunks. Okay, so basically in this function what we do is we read every page of the PDF, and here we combine it into one single big string, right, over here in full text. Then we open a window across this full text, and we say that each window is one chunk. So also this overlap here, it means that each chunk shares a few characters with the previous one, so that when we make cutting, it doesn't just cut off randomly. So also now that we have loaded our documents, we need to also go to embedding, which is the next step. So basically we need to find a way to search these chunks by meaning, right? Not just by their keyword. For example, if we ask, what's the capital of France, for example, the string needs to find a chunks about Paris, even if they don't contain that exact wording. So this is how we do it with embeddings. Basically, an embedding is just a list of numbers, like a vector, and this vector, it represents the meaning of a piece of text. So basically, if we say that text with similar meanings, they will have vectors that are close together, that overlap together in space. And the model we're going to be using to generate these vectors is OpenAI's model. Now, obviously, you can also use another model if you prefer. So basically, now can come down here, and let's actually import also the OpenAI library that we used. So we write from OpenAI import OpenAI. Okay, so now we come down here and we can start the code. We first need to initiate the client. So we say client equals OpenAI. Then we make the function. So define get embeddings or embedding text, which will be the import that we use. And so let's say response equals client dot embeddings dot create. So now we set the model. We set to say model equals text embedding very small. Then we use input, which will be our text in the parameter that we'll give. Okay. So now we can come down here and return the response data. 0.embedding. Now we need to make a second function. Define embed the chunks. Right? And as an input parameter, we'll just put the chunks again. So first we need to print that this function has ran correctly. So we start with embedding chunks. Then we set the list again for embeddings, and we set it empty for now again, which will start incrementing with a loop. So for I dot I chunk in enumerate chunks let's say embedding equals get embedding from the chunk. Then embeddings dot append embed, right? So we just append to the empty list we just created. Then we say if I, so if it's divisible by 10, print if let's say I, and we divide by length. Chunks. Done. Right? We print it. Then finally we return embeddings outside the loop. Okay, so now basically here each embedding is a list of, let's say, 1500 numbers, right? And that's the size of vectors space for this model. So we're creating basically one embedding per chunk. So now that we have the embedding, we now need to store somewhere these embeddings, right? We need to store them so that we can search for them later on. And in production, we most likely would use a vector database like, for example, Pinecone or Chroma. But since we're doing it from scratch here, we can just build one using NumPy. So come down here. So we're gonna, since we have imported NumPy, oh actually we have to import NumPy as, let's say, NumPy as NP, okay? So now we can use the library of NumPy. So we make a class, we call it, let's say, vector store. And we define in it self okay, so self.chunks. Again, we set the empty list. Then we say self.embeddings, and we set the empty list. Then we need to write the functions for this. So we'll just add like add function firstly. So define add self. We need to add chunks and embeddings. So self.chunks equal to chunks, and self.embeddings equals to the NumPy array we'll use for the embeddings. Then we need to define a function to see their similarity. So in this case, we're going to be defining a function called cosine similarity. Similarity self A and B. Then we return basically NumPy dot A and B divide by NumPy linear algorithm norm A basically times by NumPy linear algorithm dot norm B. And now we make the function for search. So define search. So we put self embedding query, call it query embedding, and finally the top key we use equals 3. And query we set to numpy.array query embedding. Now we set their scores. So let's make it here self dot cosine similarity. We use query and embedding. Then we use for embedding in self.embeddings. We run this loop. And finally, we set the top indices equal to np argsort. So we sort based on the scores first, right? So we can compare their similarity in the search. So it's -1, and we take top k. And finally, we return it. Return self.chunks I for I in top indices. Okay, so basically in this whole class, the key function that we're going to be mainly using is the cosine similarity, because it will, since we're using vectors, we need to measure the angle between the two vectors, right? So if two vectors are both pointing in the same direction, that means they are similar. So especially in cosine, the cosine similarity must be close to 1. And if they point in opposite directions, then it will be close to -1. So for example, when we ask a question, we embed this question, then we compare it to every chunk embedding. And over here, since we have top k equals 3, we'll return the top 3 most similar chunks. So it's actually very simple, but really powerful function to have. So quick recap so far. First, we get the PDF, right? We load all the text from it, and we split it into overlapping chunks so that nothing important will be cut off, right, from the edge. Then we saw the embeddings, where the text pretty much gets converted into vectors of numbers that represents the meaning of this text. And the model we used here was OpenAI's embedding model, which will convert every single chunk into one of these vectors. And basically, if you get any document prepared and embed it, as long as it's embedded, you can easily be able to search it. And finally, after we embed it, we built these vector store, right here, the class vector store, which will hold all these embeddings, and it will allow us to search through it, add to it, and compare their similarities. And the next step here would be to write a search function that finds the most relevant chunks for any question, and then we connect it basically to an LLM, and it will actually answer the questions of these. It will actually answer the most relevant questions, right, about our document. If you guys have any further questions, please let me know down in the comments below. And finally, if you guys found this video helpful, please make sure to like and subscribe, and I'll see you guys in the next one.